Okay, so I'm going to do a power factor correction question. This would be one that's right out of your blackboard, so it should be indicative of what you're going to see on your blackboard. So we have a motor that draws 18 amps at a power factor of 55%. Yeah, that's something maybe new. We're just going to change that to a decimal, so it's power factor of 0.55. It's a lag, is connected to a 240 volt 60 hertz supply. A capacitor is to be connected in parallel with the motor to correct the overall power factor to 0.95. The capacitor will need to have an XC of. Okay, so first thing we're going to do is set this up just like a parallel, because these devices are in parallel with each other. So they've given us amperage, so we're just going to start with our current section, and we have our motor. And we were going to have a capacitor bank or capacitor that's going to correct our total to a different power factor. So our motor has a power factor again of 0.55. The capacitor is going to have a current value, and then we're going to have a total, and the total is going to be corrected to 0.95. Okay, so that's kind of where we're at. We're going to start with a motor that has a very poor power factor. We're going to put this capacitor in parallel to try and correct it to 0.95. So I'm going to put 18 amps here because that's what the motor's drawing. And then I'm going to be able to start using my power factor here to solve for my reactive portion of current. So I go 18 times 0.55 and I get 9.9 amps here for the resistive portion. When I want the reactive portion of current, I just go 18 squared minus 9.9 squared, and then take the root, and I get 15.033 amps here. So now in these types of questions where they've given you a power factor to correct it to, the only thing we can bring over to this triangle is the resistive portion of current, okay, or the in-phase portion of current. Because we're going to be changing the reactive portion of current by changing this value by adding a capacitor in parallel. So we can bring this guy right over to the bottom here and put 9.9 amps right there. Then I can solve for my new total line current. So I go 9.9 divided by 0.95 and I get 10.421 amps. Okay, so that's what the line current's going to be. So we can already see a difference. This motor's drawing 18 amps. Well, when we correct it to 0.95, the system is only going to have a 10 amp draw. So that's a significant amount of current difference. Okay, so now we're going to find the reactive portion, the new reactive portion of current once we correct it. So I'm going to take that 10.421 squared minus 9.9 squared, and then take the root, and I get 3.254 amps here. So what that means is this is still due to a lag because we corrected to a 0.95 lag. This value here is what's left over from this value once we added, or I guess in all fairness, once we canceled these out with this. Okay, so we are adding them, but they're 180 degrees apart, so they cancel each other out. But basically, we need to be able to find this. So if I know this minus this, because again they cancel out, equals this, to find out this value here, I can just subtract. So if I go 15.033 minus 3.254, I get 11.779 amps here. So that's the current draw of the capacitor. So now it's telling me it wants the XC. So I didn't leave myself room for an impedance section here, but we can just use Ohm's law to find that out. So I have a supply of 200, so I'm looking for my XC. So I can take my 240 volts divided by 11.779 amps, and I'll get my ohmic value, which in this case is XC because it's a capacitor. So 240 divided by 11.779, and I should have a ohmic value, or an XC, of 20.375 ohms. Okay, so that's what the capacitor bank would have to be rated at in order to correct this 0.55 motor, okay, from drawing this current at this power factor. we're not changing the power factor of the motor. Okay, we can never change the power factor of the motor unless we would rewind it. Okay, it runs at that power factor and it draws that current. What we're doing to reduce this line current is we're dealing with the VARs. Okay, again, the VARs are the part that for a magnetic field to be created, power that we don't necessarily want, but we have to deal with. So we're going to feed these VARs from the capacitor rather than pulling it from the source, and that allows us to drop this current here. Okay, so that's the whole point of power factor correction, is to reduce this line current. If we reduce the line current, we can reduce the size of the conductors, we can have more room on our supply transformers for more, basically more supply. Again, these are small currents, but these could be up to, hundreds of amps, okay, on a service. Okay, so that's kind of the whole point of power factor correction. Take a very poor power factor piece of equipment, or even a whole plant or a whole shop, and then add a capacitor bank to correct it and reduce our line current coming in. Okay, so hopefully that helps. I'll do another one here and go from there.